When you look at an electronic capacitor storing a charge, an OLED screen emitting light, or a prism separating a beam into colors, you are observing different applications of material physics. Engineers govern these technologies using macroscopic constants. They use relative permittivity to measure electrical storage capability and refractive index to calculate optical manipulation. But neither of these constants is a foundational property of nature. They are macroscopic approximations. At the microscopic level, both of these physical behaviors trace back to a single variable, molecular polarizability, denoted as alpha. If we measure exactly how a single molecule's electron cloud responds to an electric field, we can calculate the absolute electrical and optical limits of any solid material. Consider a single molecule resting in a vacuum, completely undisturbed in its quantum ground state. When we apply an external electric field across this space, that field acts as a perturbation. It actively pulls at the molecule's resting energy structure. This equation shows the quantum Hamiltonian perturbation. The original energy state is modified by the external electric field and the dipole operator. This external force forces the ground state to mix with higher energy excited states. As a result, the electron cloud shifts its physical geometry. We call this geometric shift the induced dipole moment. The proportionality constant that determines exactly how easily this electron cloud deforms is alpha, molecular polarizability. Looking at the math, polarizability scales up massively when a molecule's excited states sit close to its ground energy level. This means its electrons are loosely held and easily displaced by the field. A molecule's electrical behavior is entirely dictated by the architecture and proximity of these quantum excited states. Because this response depends on the electron cloud, the physical structure of a molecule strictly controls how it reacts to an electric field. Every molecule experiences electronic polarization, the instantaneous physical distortion of the electron cloud relative to the central nuclei. For a nonpolar molecule like benzene, this is the only reaction. Because it lacks a permanent dipole, the electric field merely forces its delocalized pi electrons to smoothly shift in the opposite direction. Water, however, is a polar molecule. When the field is applied, water undergoes electronic polarization, but it also experiences orientational polarization. The entire molecule must physically rotate to align its permanent dipole with the external vector. Because orientational polarization requires moving actual physical mass, it carries a distinct vulnerability: temperature. This equation illustrates the relationship. Orientational polarization is inversely proportional to the Boltzmann constant multiplied by temperature. Thermal motion violently shakes the molecules, constantly breaking their alignment with the field. Therefore, a polar material's electrical capacity decays exactly as its physical temperature increases. If we scale this up from an isolated molecule to a dense macroscopic lattice, we introduce millions of active dipoles working simultaneously. This equation defines macroscopic polarization, or vector P. It measures exactly how much dipole moment exists per unit volume of the bulk material. The electric susceptibility term links directly to the dielectric constant, also known as relative permittivity. This determines how strongly the entire material responds to an electric field. A high permittivity creates immediate physical consequences, like charge screening. Take two interacting point charges, a sodium ion and a chloride ion, attracting each other through a vacuum. Drop these ions into a high permittivity medium, like water, and the surrounding dipoles immediately align. They generate opposing internal fields that violently dampen the main attraction between the sodium and chloride. The dielectric constant is the physical measure of a material's ability to cancel out external electric fields using its own internal geometry. This entire framework assumes a slow, static electric field. We must now account for the variable of time. What happens when the driving electric field oscillates rapidly? This equation represents a high-frequency alternating field, such as a light wave. To measure the material's response at these speeds, we use dynamic polarizability, expressed as a function of frequency. At optical frequencies, a physical limitation emerges. Massive molecules simply cannot physically rotate fast enough to track the rapid changes of the driving field. Because physical rotation fails entirely, the orientational polarization drops to zero. In this optical regime, the entire material response relies solely on the near-instantaneous electronic polarization of the outer shell. To calculate how light interacts with matter, we abandon physical rotation completely and rely on high-speed quantum distortion of electron clouds. This high-frequency electronic polarization dictates a macroscopic property you already know, the refractive index. As the oscillating electric field of light drives the electrons, those electrons form induced dipoles. These dipoles then re-radiate their own electromagnetic waves, which interfere with the original light wave, altering its phase and reducing its transmission speed. This equation shows the full quantum expression for dynamic polarizability. Pay close attention to the denominator, where the incoming photon energy subtracts from the transition energy gap. A resonance condition occurs when the incoming photon energy perfectly matches the transition energy gap of the molecule. In the stable region of the curve, we see normal refraction. The light merely slows down as it propagates through the material. But near resonance, the denominator approaches zero. The refractive index behaves radically. The molecule heavily absorbs the energy, and light transmission is destroyed. A material's refractive index traces a dynamic curve dictated entirely by how closely light's frequency matches the internal quantum energy gaps of its atoms. This is the Lorentz-Lorenz relation. It completes the loop, directly connecting microscopic dynamic polarizability back to the macroscopic optical properties of the bulk material. Mastering this specific causal chain is the foundation of modern optical and electronic engineering. Whether an engineer is tuning relative permittivity to control exciton binding in an organic solar cell, or modifying the refractive index for optical outcoupling in a display screen, they are solving the exact same physical problem. Macroscopic electrical storage and optical refraction are the exact same phenomenon, the precise quantum manipulation of the electron cloud.